Good afternoon, I'm Guidry. I'm with Group 2 and I'm the lead for the Reynolds number testing. So the objective of this project is to experimentally determine the flow rate at which the internal pipe flow is laminar, transitional phase, or fully turbulent. The flow rates can then be used to determine the Reynolds number. This will be conducted for a pipe and rectangular duct, also known as the hydraulic diameter pipe. The second part of the experiment is to determine flow rate using a differential pressure transducer before and after an orifice. So some background and theory on this. A Reynolds number is a dimensionless quantity. It can be used to help predict the type of flow occurring inside of the pipe. Laminar flow is a stable flow and it typically has a Reynolds number less than 2,300. Transitional flow is a mix of laminar and turbulent flows, and its Reynolds number is typically in between 2,300 and 4,000. Turbulent flow, it's an unpredictable flow due to its flow vortices and eddies, and it has an average flow rate is what you use to calculate the Reynolds number, and it's going to be greater than 4,000. So the turbulent flow is going to be mixing around. You see a lot of mixing, it won't be just a smooth pipe flow. Here's the apparatus for the experiment. Right here you can see the three different pipes. Starting from the front, you got the Reynolds number pipe. Then in the middle, you have the hydraulic diameter pipe, which is the rectangular tubing. And on the back side, you have the orifice pipe, which is the same as the Reynolds pipe. It just has an orifice right in the middle. This is the computer that's used to control the valves, which control the flow rate, and also take the measurements. Here are the computer-controlled valves, which allow you to manipulate the experiment. So I'm just going to go over like a quick procedure for this experiment. Basically, you run three different experiments. The first one's on the Reynolds pipe, second one hydraulic diameter pipe, which is just square tubing, and the orifice pipe. For each experiment, the computer used to control the flow and collect the data. For the Reynolds and hydraulic diameter experiment, the flow rate starts low, and you inject the dye, and you see how the dye acts in the flow. And then you incrementally increase the flow to observe what's the flow rate when you get to transient flow and turbulent flows. For the orifice pipe experiment, you're going to take the pressure difference from the pressure transducer for 10 separate flow rates. And for the Reynolds and hydraulic diameter, you do it 5 different times and take the average. This is from the lab manual, and this shows examples of laminar flow, how the dye results should look. This is for the transitional flow, also known as the Helmholtz instabilities, and the dye bursting dye cloud. That's when you get turbulent flow. Some of the equations used in this experiment is the Reynolds number equation, which is the density times velocity times the hydraulic diameter divided by the viscosity. To determine the hydraulic diameter, it's 4 times the area, cross-sectional area divided by the wetted perimeter. And then for orifice flow rate, you got K, which is a constant, the area, cross-sectional area of the orifice, your change in pressure, and the density of the fluid. Quick example calculation that I did for the Reynolds number, plugged in the density of water, hydraulic diameter head, viscosity, and with a flow rate of about 0.04 meters per second, you'll get a Reynolds number of approximately 2,300. Quick hydraulic diameter, I did it for our rectangular tubing, and it's multiplied out to get the area 2 times the length and the width will get you the perimeter, and you get an equivalent diameter of 0.02. For orifice flow rate, the 0.8 constant was given in the lab manual for an orifice, and then I did the area of the orifice, here, and then the density of water, and I estimated a pressure difference of 5 pascals, so I better get a result. And then you get a volumetric flow rate of about 2.29 times 10 to the negative 6. I tried to predict the results of which flow rates you should see laminar flow, where it's going to transition, and then when you should see the fully turbulent. For laminar flow, for the velocities of 0.0465 and less, the transitional flow rate should be 0.0465 to 0.081 meters per second. And then for turbulent flow, anything over 0.081 meters per second. Are there any questions?
Does the temperature of the liquid matter?
It would matter in the viscosity of the liquid. So I mean, it will play a part if it's super cold or hot or room temperature. But that would come in for the Reynolds number in the viscosity.
And if I change the shape of the pipe, you gave a range initially, right? 2,300 to 4,000.
Right.
Will that change if I change the shape of the pipe?
It shouldn't change for these calculations because you're doing the hydraulic angular equivalent. So you're basically converting the square pipe to a circular pipe with this formula, so it would be the same.
If you're at different pressure, will that change how fast the water needs to be moving to get the equivalent of for turbulent or any other flows like that?
Which means for the orifice one or just for the Reynolds number?
Just for the Reynolds.
So if you got different pressure, it's going to change your flow rate if you change the pressure. And then for the Reynolds number, you're looking at the flow rate. So if you're changing pressure, the flow rate is going to change, which is going to cause it. For this experiment, we want to try and keep it constant flow rate and then just keep incrementally making it higher and higher so you can see when the dye changes like the examples. Any other questions? Thank you.